After a century of searching, scientists find new liquid phase. Researchers at the University of Colorado Boulder's Soft Materials Research Center, SMRC, have discovered an elusive phase of matter, first proposed more than 100 years ago and sought after ever since. Now, before we start, make sure you hit the subscribe button, and if you already did, do click on the bell button so that you will not miss out any of our new videos. The team describes the discovery of what scientists call a ferroelectric nematic phase of liquid crystal in a study published today in the Proceedings of the National Academy of Sciences. Co-author Matt Glaser, a professor in the Department of Physics, said, "The discovery opens a door to a new universe of materials." Nematic liquid crystals have been a hot topic in materials research since the 1970s. These materials exhibit a curious mix of fluid and solid-like behaviors, which allow them to control light. Engineers have used them extensively to make the liquid crystal displays, LCDs, in many laptops, TVs and cell phones. Think of nematic liquid crystals like dropping a handful of pins on a table. The pins in this case are rod-shaped molecules that are polar, with the blunt heads that carry a positive charge and the pointy tails that are negatively charged. In a traditional nematic liquid crystal, half of the pins point left and the other half point right, with the direction chosen at random. A ferroelectric nematic liquid crystal phase, however, is much more disciplined. In such a liquid crystal, patches or domains form in the sample in which the molecules all point in the same direction, either right or left. In physics parlance, these materials have polar ordering. Noel Clark, a professor of physics and director of the SMRC, said that his team's discovery of one such liquid crystal could open up a wealth of technological innovations, from new types of display screens to reimagined computer memory. Clark said there are 40,000 research papers on nematics, and in almost any one of them you see interesting new possibilities if the nematic had been ferroelectric. Under the microscope. The discovery is years in the making. Nobel laureates Peter Debye and Max Born first suggested in the 1910s that, if you designed a liquid crystal correctly, its molecules could spontaneously fall into a polar ordered state. Not long after that, researchers began to discover solid crystals that did something similar. Their molecules pointed in uniform directions. They could also be reversed, flipping from right to left or vice versa under an applied electric field. These solid crystals were called ferroelectrics because of their similarities to magnets. In the decades since, however, scientists struggled to find a liquid crystal phase that behaved in the same way. That is, until Clark and his colleagues began examining RM734, an organic molecule created by a group of British scientists several years ago. That same British group, plus a second team of Slovenian scientists, reported that RM734 exhibited a conventional nematic liquid crystal phase at higher temperatures. At lower temperatures, another unusual phase appeared. When Clark's team tried to observe that strange phase under the microscope, they noticed something new. Under a weak electric field, a palette of striking colors developed toward the edges of the cell containing the liquid crystal. Clark said it was like connecting a light bulb to voltage to test it but finding the socket and hookup wires glowing much more brightly instead. Stunning results. So, what was happening? The researchers ran more tests and discovered that this phase of RM734 was 100 to 1000 times more responsive to electric fields than the usual nematic liquid crystals. This suggested that the molecules that make up the liquid crystal demonstrated strong polar order. Clark said when the molecules are all pointing to the left, and they all see a field that says, "go right," the response is dramatic. The team also discovered that distinct domains seem to form spontaneously in the liquid crystal when it cooled from higher temperature. There were, in other words, patches within their sample in which the molecules seemed to be aligned. Clark said that confirmed that this phase was, indeed, a ferroelectric nematic fluid. That alignment was also more uniform than the team was expecting. Joe McLennan, a study co-author and a professor of physics at CU Boulder, said entropy reigns in a fluid. Everything is wiggling around, so they expected a lot of disorder. When the researchers examined how well aligned the molecules were inside a single domain, McLennan said they were stunned by the result. The molecules were nearly all pointing in the same direction. The team's next goal is to discover how RM734 achieves this rare feat. Glaser and SMRC researcher Dmitry Bedrov of the University of Utah are currently using computer simulation to tackle this question. Clark said this work suggests that there are other ferroelectric fluids hiding in plain sight. It is exciting that right now techniques like artificial intelligence are emerging that will enable an efficient search for them.